So this is a PSIM which is available for the student use as well. You can download the demo. Let us draw an H-bridge square wave inverter here and try to simulate it to find out the harmonic content and the shape of the current that flows through the switches. So here we have a VDC available. Let us put it here, and then we have some switches available here. So let me choose this MOSFET here and create an H-bridge. Also, we need to find out what is the current flowing through the source. This is the current flowing through the source. We need to find out the current through the load, and also we need to find out what is the current which is flowing through these pair of switches. Because we need an inductive circuit, so this is the resistance here. We have inserted the resistance, and this is the inductance here. We can move it a little bit on this side, and then with using this wire connection tool we can connect these switches. Also, we need to see what is the load voltage. So for that we can connect it somewhere here, and then we can say this is these are markers to show it on the oscilloscope. Let us say this is IDC, this is IS1, and of course this is IS2. This one will be IS3 and IS4. IS3, IS4. We have to select 100 volt as this for this DC. The resistance is this 10 ohm, and the inductance part is 25 millihenry. So if we write it with 25 with the small m, it will automatically detect that this is actually a 25 millihenry inductor. To turn on these switches, we will use this simple gating block. If we double click on this, we can adjust, because the frequency is set to be equal to 60 Hertz, and this is for 1/2 cycle. So we can just simply use it for this diagonal pair. For the negative half cycle, we need to change this from 0 182, 100 and 182 and 360, so that it represents the turning on of the switches for the rest of the half cycle. So now we further need to have a simulation control here. Let us run the simulation for 0.1 second, and we turn on the simulation. Now that we have this simulation available, so let us first say this is not V0, this is V0, which is the output voltage. I forgot to write it here, and this is the I0, which is the output current. So let us simulate it again. Now we have this available. This is the V0. That is the job of a square wave inverter. So we have 100 volt available when we are turning on the switches S1 and S2, and we are getting minus of 100 volt when we are turning on the switch S3 and S4. In addition to that, if I plot it over this particular waveform, the output current I0, so you can see here that is I0 is having a value of the same shape that we have earlier discussed in the theory. In addition to that, let us draw the current which is flowing through the IS1 and IS2. So you can see here, this is the current which is flowing through IS1 and IS2, and because of this negative part here, we have earlier stated that a bidirectional switch is required. A switch is required which can allow the flow of current in both the directions. Similarly, if I plot it for the other two, you can see here that for this duration, the other two switches actually conduct. Additional to that, we want to see what is the DC current IDC which is flowing here. So you can see here, this is the shape of the current which is flowing here. So let me show you the value which is equal to 4.63. so this IDC that we calculated here, we calculated the IDC, and that was equal to 4.41 ampere. So here we can see here that we have a slight little bit of variation because of the simulation settings. However, it is approximately the same. In addition to that, let us find out the let me delete these graphs here. And okay, so now we have only the voltage and the output current. So let me delete this output current as well. So now we are left with only this square waveform. So if I take the Fourier transform here, and that too for up till the 9th harmonic for a 60 Hz waveform is 540. So let us bring it to 600 Hertz on the x-axis. So you can see here that we have the fundamental component, which is at 60 Hertz. This is the frequency which you can see here, is 60 Hertz, and it is calculated to be equal to 127 volt. So during our simulation, during our analysis of the Fourier, we computed this V1 equal to 127.38. Similarly, if we go ahead and we move on to the next harmonic, which is the you can see here it is at 180 Hertz, which means it is the third harmonic. So we have computed the V0 equals to 4.24, and 4.24 is for 1, so that is equal to 42.4 volt, and that is what we have calculated here. Similarly, for V5, the voltage which is shown in the simulation is 25.47, as you can see here, and you can see this is 25.46. And for the next frequency component, which is the 7th harmonic component, the frequency is 420, and we have 18.19 volt available, which is available here, 1.81 into e to the power 1. So if we move on further to see what is the last frequency component we have selected, it is approximately equal to approximately equal to 14.14. Of course, the simulation provides us a lot of information about the behavior of a system with respect to the total harmonic distortion and other useful information we have seen here. That's all for today's lecture. Thank you very much.